All right, welcome back. Today we will talk about the surface energy for two phases, interfacial energy for two phases. Let's think about two phases um, uh, like this, and there is a flat interface between them. Now, flat interface meaning the radius of curvature is infinite. Now, what is this radius of curvature? When you say, uh, let's say there are two surfaces like this, which one has higher radius of curvature? Then, of course, it's this one, right? Oh, wait, no. This one has higher radius of curvature. This one, so R is proportional to reciprocal of curvature like this. So this one has higher curvature because the R is here. This is R. This is R here for this one. Obviously, this one has higher radius of curvature, meaning smaller curvature. Okay? So for this system, we can use dg equals mu I dni plus mu 2 dn2 plus gamma dA. This this formula equation is coming from this dg equals STT minus VDP minus STT plus VDP plus mu dn plus gamma dA. Now we have both constant temperature and pressure. So we're left with this. That's where it comes from. I mu I dni plus gamma dA. This is where it's coming from. Okay? Back to this model here. Okay? This is how you describe this model. Then, when this model is in equilibrium, so of course this is a surface that is naturally formed between phase 1 and phase 2. Okay, if you mix, let's say these are A atom, these are B atom. If you learn phase transition, then if you mix them, then it will naturally form alpha form. This is alpha form. These are beta form, and this can be maybe FCC like this. No, FCC, okay, like this. It is formed like this, and this one is BCC. So two different crystal structure, and two phases are formed by simply mixing these two A and B. Okay, and it's a spontaneous process, so it will the ratio of alpha So when you draw a eutectic diagram like this, so here in this particular temperature, you can use at this particular x alpha. So this is how much of B you mixed inside A, okay? This is how much XB this is the molar fraction. Let's say you added 30% of B and 70% is A. This is what this point indicates. Then you can use lever rule, right, to calculate how much fraction of alpha phase and how much portion of beta phase is coexisting at this temperature. And this how much is simply varying with equilibrium. Do you understand what I mean? So at this amount of B and at this temperature and certain pressure, this lever rule is achieved by equilibrium, okay? And that equilibrium is coming from this equation. So when this equation dg becomes 0, it will reach equilibrium and achieve this graph, so we can calculate using lever rule, okay? Which means before equilibrium, this surface is movable. Movable meaning amount of I and amount of 1 and amount of 2 are changing. So if amount of 1, they mix, they form. Okay, let me use this. So changing meaning amount of 1 is increasing, right? So you mixed some B, amount of alpha phase. Let's say this is alpha phase, this is beta phase in this picture. Then when you mix, alpha is forming, beta is also forming, and this phase, this boundary here is the boundary here, and it is moving like this. So they are competing. If alpha is forming faster, it will move more to here. If beta is forming faster, then it will move towards this direction like this. So that is the concept here. And at equilibrium, it will stop like here, at here. So meaning that we can rearrange this equation to become like this. dg equals mu I dni plus mu 2 dn2 plus gamma dA, and equals to 0 because it's at equilibrium. Okay, then mu 1 dn1 plus mu 2 dn2 plus gamma dA is 0. And here the total amount of Ni plus N2 is N. So here, even though this is changing, and this is becoming 1, like the phase is moving, meaning that this amount of 2 became 1, alpha phase. But alpha phase add a number, and the number in beta phase, if you summation, then it's staying constant because conservation of mass. The total mass inside the system is not going to change. So this equation, right? And you can get another equation from this. That is dn equals to 0. And equals to constant. So dni equals to dn2. So amount of n2 that became n1 will result in amount of ni that came from n2. That's what this equation means. Okay? Amount of n2 that has become n1, meaning amount of new n1 that is coming from n2. So you have a minus here. But also you can simply rearrange this equation and get this. That's the mathematical way. This is the physical way to understand it. Anyway, so back to this equation. You plug this in, then you get this. Mu I minus mu 2 equals to gamma dA. You divide both sides by dn2, right? Then you will get, mu 2 d and mu I equals to gamma dA divided by dn2, right? Because you divide both sides by minus dn2. So mu minus dn2. Wait, you divide both sides by dn2. Right. Sorry, let's just do it. Sorry, this is confusing. If you divide both sides by dn2, then it will be like this. Minus mu I plus mu 2 plus gamma dA divided by dn2. If you divide both sides by dn2, then equals to 0. Then rearrange it. Mu I minus mu 2 equals to gamma dA dn2. Then, because it is a flat surface, right? So no matter how dn2 change, this amount of area is going to stay constant, meaning dA equals to 0. So whenever something stays constant, you can note that the derivative of it will become 0 because it's constant. So mu I equals to mu 2 because this is 0. This is 0, so mu I equals to mu 2. So you could see that whenever two phases with flat interface are in equilibrium, then the chemical potential of them will be the same. All right? Now, what will happen if it's a curved surface? Curved surface. Then you can also get from this equation, what was it? Gamma dA divided by dn2. Then obviously you just have to modify here, right? Because everything else is the same from this equation. dn mu I dni plus gamma dA Okay, everything else is the same. You just have to modify here. It won't be like 0 like in the flat surface because it has different radius of curvature, right? Then you just have to modify there. So how are we going to do that? Well, we are going to use this equation. V equals to divide by, and this is molar volume. Then V wait, dA right. Wait. Sorry. All right. Yes. Then N will become like this, right? So you plug this in here. Then dN will equal to dV divided by this. Then you plug this in, mu I minus mu 2 equal to gamma dA divided by dV times V, like this. And you can see that A equals to omega r squared, and V equals to what was it? Yes, here. Omega r to 3. Okay. Then if you plug this in, dA equals to 2 omega r dV dr. dV equals to omega r squared dr. If you plug it in, then it will become like this. 2 equals V. If you calculate it, it will be like this. So if you rearranged it, then 2 gamma divided by r. Okay, so you get it. So whenever they have a curved surface at like a surface with curvature r, radius of curvature r, then at equilibrium you can get this kind of formula. So this is the curvature of the surface, the radius of the, so at equilibrium this r is the radius of curvature of the surface at equilibrium. Then you can get the difference of chemical potential between them. All right. So much for our lecture today. Next lecture, we are going to talk about vaporization or sublimation of and then how are we going to calculate that? Okay? Thank you.